today.
And real quick, Dave, can you see my screen?
Yes, I can, John.
Excellent. All right, well, with that, we'll go ahead and get started. Hello, everybody, and welcome to our tutorial today detailing how groups could effectively verify high-level synthesis-based designs using established and understood verification methods. We're going to be spending the next 45 minutes or so reviewing these techniques and talk about how they were applied to verify a machine learning accelerator design, all of this prior to sending the design through synthesis to produce the RTL. And in case you missed it, my name is Jonathan Kraft. Dave Arney and I are both technologists specializing in high-level verification, working for Siemens EDA.
Hi, this is Tom.
Oh, hey, Tom. All right, so during this session, we'll be focused on high-level verification, or HLV, and how that fits into an overall high-level synthesis design methodology. We will begin by trying to answer the question of why. Why do we do high-level verification? Talking not just about its benefits, but also the tools and the capabilities that are present within the Catapult design verification flow that enable it. We will then show how these capabilities can be applied to a machine learning accelerator design in order to not only validate the design's functionality, but also to prove that the design's performance goals have been met. We'll be doing all of this using techniques that many of you should already be very familiar with as verification engineers, but we'll be targeting the pre-HLS source code that was written in System C instead of the post-HLS RTL. Because the bulk of our verification is done against the pre-HLS source, there won't be much left to do after high-level synthesis, but we will go over what that would look like as well before we wrap up the tutorial. So before we jump into high-level verification, we should talk a little bit about the question of why. There is a constantly evolving and improving set of design tools that are enabling us to produce larger and more complex designs year over year. Examples like growing libraries of available design IP, design automation systems like the ARM AMBA Designer, HDL generation tools like Chisel and Scala, and of course, more abstract design synthesis tools, such as Catapult, are all contributing to this trend towards bigger and more complex systems. On top of raw size and complexity, these designs are burdened with more requirements, such as improved power, performance, and area, or PPA, and safety and security requirements. All of this new design output needs to be fully verified before going to silicon, and this is where groups are struggling to keep up. Verification productivity is being outstripped by design productivity, which, if left unchecked, renders many of these design improvements less useful. Verification techniques must evolve along these design techniques, and this is where HLV fits in. So here we show a traditional RTL design and verification flow. It begins with architecture and algorithm development, only after which can design teams start putting together RTL blocks, and verification teams can begin developing test benches and writing tests. Once the RTL has reached a certain level of maturity, RTL verification and debug begins in earnest, ultimately resulting in design sign-off. In contrast, the Catapult HLS flow enables architectural and algorithmic exploration in parallel with the development of verification infrastructure and testing, long before any RTL is produced. And all of this is focused on a more abstract version of the design, typically leading to faster simulation performance and easier debug. Overall, this typically results in at least a 50% faster development cycle compared to the traditional RTL-based flow. In its own right, high-level synthesis comes with all sorts of productivity benefits on the design side. As a designer, it allows you to define very complex algorithms in more compact and a more abstract language. And it enables you to rapidly explore different ways to implement your algorithms in order to find the best possible combination of PPA, or power, performance, and area. Going beyond these benefits to the design process, there are also several advantages to verification when it comes to high-level synthesis. Purely from the aspect of performance, System C-based simulation has been shown to be about 300 times faster than equivalent RTL sims. With timing accurate modeling in place via something called matchlib connections, and I'll talk about that here in just a bit, things do slow down for the sake of better accuracy, but we're still talking about 30 times faster than RTL. The table on the right here highlights the performance measurements that we took from our machine learning accelerator design and test bench. The pre-HLS simulation that targeted the System C version of the design took about 20 minutes to run, whereas the equivalent post-synthesis RTL took about 30 times longer to finish. These gains in performance versus RTL simulation are fundamental to why HLV can be so powerful. The ability to run simulations so much more quickly enables more comprehensive overall verification against that pre-HLS design. Now, we do recognize that RTL verification sign-off is still very much a requirement, but we want to do whatever we can to make that RTL level verification as easy and as predictable as possible, and performing as much of the design verification as possible against a faster version of the same design helps to ensure that predictability. So how do we achieve this? Well, much of what I'm describing here should be very familiar to most of you. We're doing most of what you're accustomed to, but with a focus on the pre-HLS design source instead of the RTL. We can leverage familiar coverage-driven and verification plan-driven methodologies that use both code and functional coverage to track progress. Furthermore, at this level of design abstraction, you will likely encounter the need not just to verify the functional correctness of the design, but you'll also be expected to verify performance concerns, so throughput, latency, and that sort of thing. Even though we're focusing on the pre-HLS design instead of the RTL, we can still use known and trusted approaches to verification, such as System Verilog and UVM, allowing you to fully leverage your existing verification expertise. This is important because it'll be too late if you simply wait for the RTL before you begin verification in earnest. The size and the scope of the resulting RTL that comes from more abstract C design source can make first level triage of test failures a good deal more difficult. And you'll likely wind up spending a lot more time throwing RTL failures back over the wall to the design team than you would like. All right, so let's quickly introduce the Catapult high-level verification flow. It starts with a C++ or System C description of the design. From there, we can carry out static and formal analysis of that design source using Catapult Design Checker. And this allows you to catch language and simple coding bugs without the need for a test bench or simulation, and you're doing this prior to running any synthesis. Moving on to dynamic simulation, which can be facilitated in a variety of test benches, C++, System C, UVM. The SV-UVM approach is what we're focusing on today. This can also incorporate third-party sources for stimulus and checking, such as MATLAB or TensorFlow. Basically, anything that you can do today in an RTL-based design verification flow, you can apply here. Regardless of which test bench platform you use, Catapult coverage can be employed to track code and functional coverage against your pre-HLS design source. This can enable you to achieve coverage closure against your pre-HLS design, working out any functional or performance bugs at this level, meaning fewer surprises and fewer debug cycles when you do move to the RTL. Once we've achieved our verification goals, we can move through the Catapult synthesis flow to produce area, timing, and power optimized RTL. Due to how we structured our test bench, you can then use the RTL as a drop-in replacement to the C design source, verifying the post-HLS RTL with the same test bench, the same stimulus and prediction, and use this to quickly achieve RTL coverage closure for the purposes of verification sign-off. And while this is outside the scope of this tutorial, Catapult Formal offers a library of formal applications that can be used to instill confidence and formally ensure the correctness of the RTL output. All right, so now I'd like to shift gears and talk about how we applied these techniques to verify a machine learning accelerator design that was written in System C. We don't have enough time today to go over this design in a tremendous amount of detail, but our verification efforts focused on an implementation of a convolution neural network that's used for object detection and classification. It was designed to run on a 500 megahertz system clock, running through 9 layers. Most of the computation and memory traffic stems from using a 3x3 convolution layer, which works out to 9 multiply and accumulates, and that works out to a total of 3.5 billion max per inference. Control and status, feature map data, as well as kernel weight data come from AXI interfaces. And this is intended to be a relatively low power, low performance design intended for a Ring doorbell type application. And we're only producing 1 inference per second. Here we have a high-level block diagram of the accelerator design itself, displaying the top level, all of which is going to be synthesized into RTL. So not the test bench, just the design. As stated earlier, this design connects to a larger system via AXI buses. Specifically, the control and status registers connect via AXI4 light bus with the design acting as a slave, and feature map data comes in from reads via an AXI master connection on the bottom. The bulk of the internal activity takes place within this conv 2D submodule, and that communicates with internal local memory that we're showing on the right. On the verification side, we're leveraging a System Verilog UVM test bench that compares our test bench output against a golden reference model. We put a test plan together that outlined our overall verification goals. This plan focused on closing code coverage against the pre-HLS source for the 2D convolution engine, which, as I just stated, constitutes the majority of the design logic and activity. The test plan also requires us to close on functional coverage goals specific to this design, such as different configuration setups and input data. Questa VIP components were used to drive AXI activity and to monitor the interfaces for protocol adherence, and to measure bus utilization. We need to confirm that the design's performance requirements of 1 inference per second can be achieved. And finally, this verification environment needs to be reusable. We want to be able to replace the pre-HLS source with the post-HLS RTL in our existing environment so that we can quickly complete our verification sign-off. So let's walk through how we applied our high-level verification flow to this ML accelerator design, starting with some static design checking. In the Catapult flow, the static design checks come in the form of Catapult Design Checker, which can be used to very quickly find errors in the HLS design source before running any synthesis and any simulation. It is possible to write your pre-HLS source in such a way as to be too ambiguous to accurately describe hardware. And Design Checker exists to detect these situations as early as possible in the design process. It consists of a number of static lint type checks, as well as a number of formal based checks that try to identify issues in the pre-HLS design source that could lead to mismatches with the RTL output, as well as issues that could prove difficult to debug during simulation. Other checks look for quality of results issues, such as suboptimal use of divide or modulo operations, or perhaps when an array size is not a power of 2. Design Checker uses formal analysis to identify out-of-bounds array reads and writes, as well as the potential for uninitialized memory reads. And all of that could result in mismatches between your pre-HLS design behavior and the resulting RTL. We organized the Catapult Design Checker checks, there's over 30 of them, into different modes. We generally align those to which phase of development the user is in. So the early phases are typically less complex and they result in less runtime, while later stages employ more complex formal checks that can take more time to run, but these are necessary when the design source is nearing its final stage and you're about to push things through the synthesis process. Regardless of which mode is being run, from the user perspective, these checks are essentially push button. The first two modes shown here, the coding checks and the Q of R type checks, are the static lint type checks. The Q of R checks do not focus on finding explicit bugs in the design source, but instead highlight areas of the design where you might be leaving potential quality of results on the table. The HLS RTL mismatch and the overflow underflow modes are where the formal base checks live, and the custom mode allows the user to enable or disable which specific checks the tool should perform for a given run. Here we're showing some results of running Design Checker against an early version of our Accelerator design. In particular, we're focusing on the results of running the simulation mismatch mode as well as the Q of R checks. The mismatch results are shown on top, and in this situation, the tool is reporting on an incomplete switch case statement. This is an example where the C simulation and the RTL could operate the same and even just fine, but the incomplete case could be masking some unintentional behavior. Fixing this could be as simple as just adding a default case. The other screenshot shows a Q of R finding, and these typically show up as warnings or infos instead of errors. Again, warning the user when their coding style could result in less than an optimal result. All of the Design Checker results can be analyzed via text reports or from within the UI. If you're using the Catapult GUI, each finding is cross-linked to the design source for easier reference. Individual firings can be controlled from a waiver file in order to reduce the output from subsequent runs. Alternatively, you can specify waivers within the pre-HLS source itself in the form of pragmas, and that's actually the preferred method for doing this. Furthermore, since this is a formal-based tool, some constraints may be needed to guide those formal checks to the correct path. And those constraints also come in the form of pragma statements in the code. These are specifically assumed pragmas. In summary, the Catapult Design Checker enables you to produce cleaner HLS design source without the need to push the design through synthesis or do any simulation, ultimately resulting in less debug of your post-HLS RTL. All right, so with a base level of confidence that our Accelerator Design's System C source is in good shape, having pushed it through Design Checker, we can move into dynamic simulation. And at this point, I expect that the flow should start to look very familiar to many of you. So we continue to leverage tried and true verification approaches by first starting with the definition and implementation of a test plan and functional coverage model, followed by the creation of tests and stimulus that carry out that test plan. Stimulus generation can use any and all approaches that you're probably already familiar with, creating of directed test scenarios, using file I/O captured from a golden model or from the lab, or generating stimulus via constrained random testing. These are all valid methods. Because we can use these tried and true methodologies like UVM to define our test bench structures, it makes it very easy to leverage verification IP off the shelf to drive standard protocol buses like AXI. Once we've defined our tests and our stimulus, we run those against our pre-HLS design. We capture our results and coverage and merge that with our test plan. And as part of this activity, we're able to collect code coverage metrics such as statement, branch, and expression coverage against our pre-HLS design as it's being exercised within our standard test bench. Between the ability to leverage standard functional coverage metrics, the usual functional prediction checking, the ability to collect and analyze code coverage from within that HLS design source itself, this allows us to achieve nearly all of our verification goals and resolve most of our design bugs before we push the design through synthesis to produce that RTL. All right, so before we go any further, we need to discuss matchlib connections. I mentioned this earlier, and I'll describe it a little bit more detail here. This is a library of commonly used functions and components that were presented by NVIDIA at DAC in 2018. It defines things like interfaces, FIFOs, and interconnect, and it includes a set of latency insensitive ports and channels along with an API for their use. And why is matchlib a key part of our HLV flow? Well, several things. Firstly, connections allows us to verify system level performance and functionality in system C. We can accurately model throughput and latency without having to drop down to the RTL level, meaning we can carry out most of our functional verification efforts against our pre-HLS design with a much higher level of performance. Matchlib also enables us to define a pre-HLS design model that is pin for pin identical compared to the RTL. And with this pin compatibility, we can take the exact same test bench environment and apply it to both the pre-HLS source as well as the post-HLS RTL. This enables us to use the same test bench environment and flow regardless of what level of abstraction defines our DUT. So let's talk a little bit more about what the matchlib connections library enables and how it works. So these ports and channels are all synthesizable and templatized for any data type that you might want to send through them. On the C side, transaction level push and pop operations are used to send data through the channels. And on the port side, a data ready valid handshake system is used, which is exposed when the synthesized RTL is generated. A simple wrapper can be used that instantiates the connections-based DUT, which exposes those data-ready valid pins at the boundary. And this is what we can drop into our common test bench environment and later swap out for the post-HLS RTL equivalent. There are several controls and debug capabilities that come with the connections library that are worth mentioning. And these make it useful beyond the performance and reuse aspects that we've already talked about. The performance benefits themselves have some controls associated with them. You can choose between a cycle accurate mode, which more closely models RTL latencies, along with a fast mode, which trades accuracy for more speed. The accuracy mode simulation is going to typically be a good deal faster than RTL simulations, and the fast mode can often run a good deal faster beyond that. From a debug perspective, you have the ability to log channel activity seen during simulation. And there are also a couple of stimulus generation capabilities worth mentioning. The first is the ability to back annotate capacity and latency information derived from the synthesis process, essentially giving these connections more accurate information about how deep FIFOs would actually be for a given channel, along with more accurate latency models associated with a given pre-HLS block. Secondly, you can automatically apply and stall conditions into your design at these channel boundaries. This essentially stresses your design by forcing upstream components to wait on sending data and putting gaps in data availability for downstream components. This would normally be something that you wouldn't be able to fully verify until you synthesized the RTL and plugged that into your test bench. But with the connections library, you can apply these sorts of scenarios to the much faster pre-HLS simulations that are available earlier in the design process. Now, as I mentioned earlier, probably the most powerful aspect of the connections library is that it gives us the ability to expose our pre-HLS design as a pin level equivalent to the resulting RTL. And this is accomplished by the creation and use of a simple wrapper, which instantiates that connections-based DUT, and it exposes those data-ready valid pins on the boundary. This wrapper is created and used automatically by Catapult, and this is what allows us to interchangeably target our pre-HLS design source or the post-HLS RTL within a standard system Verilog or UVM test bench. Shown here on the lower left is the top of the file defining the top level of the connections-based accelerator design. You can see a couple of SC ins for the clock and reset, but also a couple channels representing AXI read and write ports. We can have Catapult instantiate that top level design within this generated thin wrapper, which binds those AXI channels to their port level representation, exposing these ports to be used in a standard test bench, such as System Verilog UVM. Which is how we get here. Fairly standard looking UVM based bench with agents connected to that pin level wrapper around our pre-HLS design using standard approaches for stimulus generation and prediction. Now, to be clear, this is vanilla UVM. There's no modifications. We're not using anything special such as UVM system C. We're not using any DPI that would be needed beyond what simply enables UVM to communicate with a simulator. This is all enabled by that generated pin level wrapper and the connections library. Once you get to this point, you have the ability to carry out a majority of your verification against the pre-HLS design, which again is available much earlier in the process and will result in simulations that typically finish a good deal faster than an equivalent RTL simulation. Once you're ready to switch gears to target the RTL instead of the pre-HLS source, doing so is as simple as compiling the RTL instead of the System C and its wrapper, similar to how you might swap your RTL out for a gate level equivalent. So let's talk a little bit about debug. But to be honest, there's really not much new to talk about here. Because we're leveraging well-established verification techniques and tools, many of the debug mechanisms that you're already familiar with at the RTL level can be leveraged here as well. You can view signals and transaction streams in your wave viewer. You can do class-based debug against your System Verilog UVM test bench code in either a post-simulation flow or interactively using breakpoints and code stepping. And of course, all of the scoreboarding and the prediction structures and all of your UVM messaging will be the same here as they would be if you were targeting RTL. So your approach to debug will generally be the same as well. I'm showing here a combination of pin level activity as well as some transaction level streams in different colors further down in the waveform. This is happening at the very start of simulation, where the design hasn't given the test bench a valid on the start signal, indicating that it's not ready to accept data yet. We can see in the transaction stream further down that during this time, there's a lot of AXI4 activity going on. And what's going on here is that the test bench is busy programming a lot of the configuration data into the DUT. So we're setting the image size, the number of feature maps, that sort of thing. And only when that's done do we get the start pulse from the design, after which the design begins to read image data from the bench. I generally find that looking at these transaction streams is by far more effective at determining what's going on and where we are in simulation than trying to decode that same information from looking at bundles of pin activity. But this is the same whether we're doing RTL or HLV simulation. The transaction streams are equally useful. Of course, with C++ or System C as our design, you can also leverage your simulator's integrated C debug capabilities as well. And because this high-level verification approach allows us to leverage the same verification tools and techniques that we'd be using at the RTL level, we can take full advantage of what standard off-the-shelf verification IP has to offer by way of debug. In this scenario, since our accelerator design uses AXI4 interfaces for both configuration and data, we used readily available verification IP from Questa to drive and monitor those buses. In addition to natively plugging into UVM-based environments such as this, Questa VIP provided a wide range of debug capabilities, including the creation of those transaction streams that I talked about earlier, a very large set of assertions that were developed directly from the AMBA specification, and some very useful text-based transaction and beat logging files that are shown here that make searching for specific address or data patterns very easy to find in a simple text editor. So now that we've built up our test bench and we're using it to stimulate and functionally verify our pre-HLS design source, there's still the question of how effective our stimulus is. And answering that question usually comes in the form of collecting both functional coverage as well as code coverage data from our tests. Now, in this environment, we can employ normal functional coverage collection since we're using a System Verilog UVM-based bench. But what about code coverage? Our design isn't in Verilog or VHDL, it's in System C. And that's where Catapult coverage comes in. That's what we're going to talk about next. This helps us understand how our test environment has exercised the design, but in the context of RTL level code coverage data, even though we're focused on a pre-HLS version of the design. So RTL code coverage and software coverage have both been around for a very long time, but they typically use different metrics and set different expectations. With Catapult coverage, we're bringing RTL coverage concepts into the HLS world, essentially treating our C++ or System C design source as a hardware representation and producing RTL-like coverage data as a result. With Catapult coverage, we can produce statement, branch, and expression coverage data based on the pre-HLS design source. We can even embed functional coverage models in our C source that will ultimately be rendered to look the same as what you'd expect to see in a functional coverage model that was written in System Verilog. We're not going to be doing that here again because we don't need to. We're using a System Verilog-based bench that has native functional coverage collection capabilities. A key thing to note when it comes to tracking code coverage against C++ or System C that's modeling hardware is to keep in mind the sorts of hardware structures that are going to be synthesized. For example, if you have a loop in your C source, that will often show up as multiple blocks of logic operating in parallel, each block running as one iteration of that loop. From a hardware code coverage perspective, just knowing that you exercised that entire loop in C is typically not good enough. You want to make sure that each iteration of the loop was fully exercised, especially if there are branches, excuse me, or conditions within the loop that will behave differently depending on which iteration of the loop that you're in. And this right here is an example of how Catapult coverage is producing HLS-aware data. The resulting coverage database can treat each iteration of these loops as separate elements, more closely mimicking how the resulting RTL coverage will look. And what this means overall is that you can focus your coverage closure efforts, both code and functional, against the pre-HLS source with the expectation of having very few surprises in the coverage area once you're ready to swap out the design for the RTL when you're doing sign-off. Each simulation involving a pre-HLS design that was instrumented for coverage will result in a coverage database, and this comes in the form of a standard Questa UCDB file. Like any UCDB, these can be merged together. We can merge them with a standard test plan UCDB and use to produce reports or view in the graphical interface for analysis and for exclusion development. Furthermore, we can leverage established approaches to do trend analysis over time and to rank test efficacy. And test ranking is extra important here because it allows us to identify which tests are closing on our coverage requirements in the smallest amount of simulation time. Remember, we're probably running a good deal faster in this pre-HLS simulation environment. So when we do eventually move to the RTL for verification sign-off, we're not going to be able to just run everything again. We're going to want to run the most effective tests that close on coverage the quickest. And ranking allows us to identify those tests very easily. So here we're showing the coverage results taken from the pre-synthesis ML accelerator design. We got here by running multiple tests using different combinations of layers, different image sizes, and feature maps. Coverage results from each run were saved and merged. Exclusions against the pre-HLS source were developed to deal with unreachable areas of the code, and our overall verification plan was incorporated in order to give us an overall view of where things stand for the entire verification effort. We also used test ranking to track which tests got the most bang for our buck for later use. These activities resulted in 100% pre-HLS design code coverage on our target subsystem, which was conv2D. Taking a step back, we can also view the overall verification plan results of the entire accelerator subsystem and test bench, looking not only at code coverage, but taking into consideration the functional coverage model, part of which we got from the use of AXI4 verification IP, along with assertions and cover directives that were present in our UVM test bench. Not shown here, but definitely worth mentioning, is that we leveraged this test bench not only to close on code and functional coverage requirements, but we also used it to very quickly validate performance requirements as well. If you recall from a few slides ago, there was an overall requirement that this design be able to perform at least 1 inference per second. Early simulations of an initial design implementation revealed that we were way off here, something like 14 seconds for an inference, requiring some very early design re-architecture. And again, the simulation performance benefits of targeting our pre-HLS design is what enabled these sorts of early analyses. Subsequent design architectures got our performance down to under 3 seconds per inference, and then refinements to that design ultimately got us underneath our 1 second per inference goal. So I hope that by now you have a reasonably good understanding of how much verification we are able to carry out against our pre-HLS design, along with the mechanisms that allow these activities to take place using methodologies and approaches that verification engineers should already be very familiar with. As a final step, I wanted to go over what remains to be done after we've gone through the HLS process and we generated the RTL. So with a majority of our functional verification complete against the pre-HLS design source, we're now ready to shift focus to the RTL produced by the high-level synthesis process. And we're going to do this by using the same bench and the same stimulus that we've already developed. So in order to understand what verification tasks remain now that we're at the RTL level, we need to understand a little of how Catapult converts abstract C++ or System C source into RTL. To that end, here's a very high-level view of how the HLS process works. So inputs include the functional description of our design in the form of C++ or System C, along with information about the desired technology library that we want to focus on, along with some number of design constraints, so clock frequency, pipeline depths, desired latency information, that sort of thing. Catapult takes all of that information and implements your desired functionality in RTL, taking into account your specified constraints to drive parallelism, such as unrolling of loops and pipelining. Catapult will build concurrent RTL based off the input C++ classes or functions. And here we see the first bit of logic that Catapult adds, state machine and weight control logic to support the desired loop unrolling and pipelining specified by those constraints. Catapult also adds I/O interfaces. We take the arguments to your C++ function calls, for example, and those are transformed into I/O interfaces, those ready data valid signals that I was talking about earlier. Catapult will also automatically infer memory and storage elements. These could be RAMs, ROMs, FIFOs, register files, that sort of thing. The output will, of course, be the post-HLS RTL, along with a bill of materials, reports, and scripts that run various flows. And when we shift focus to verifying the RTL and closing coverage on this, it's this newly added logic that I've highlighted here that may require us to go beyond what we've already developed at the pre-HLS level when we're testing the post. So as a brief recap, we've already achieved our coverage goals against our pre-HLS design source. We've hit all of our code coverage goals along with checking off everything in our verification plan. And this is where we can start to recognize the benefits of reuse and test ranking. The entire test bench environment that we developed for and used against our pre-HLS design can be reapplied here with a focus on the RTL elements that Catapult added to the post-HLS design. Furthermore, we probably don't want and don't need to run every single test again, as we no longer get to enjoy the performance benefits of targeting that pre-HLS design source. Instead, we can track the test results from our pre-HLS verification and apply only the most effective test vectors against the RTL. And this gets us to a baseline of code and functional coverage as quickly as possible. Typically, what remains at this point will be associated with those new items that Catapult added, and Catapult provides automation in these areas to help you address these remaining coverage holes. This automation comes in the form of automatic stall and reset testing, similar to the random stall injection that I talked about earlier with MatchLib connections. But instead of applying it to connections channels, we are instead applying random stalls to the actual ready and valid pins in the synthesized RTL. On top of that, we can apply formal reachability analysis against the RTL to automatically generate code coverage waiver files that can be applied against our RTL code coverage data. So unfortunately, we don't have time to go into a lot of detail regarding how all of the code coverage closure activity played out against the Accelerator design RTL, but I did want to go over the results after the different steps in the process were taken. One test in particular from the high-level verification stage was ranked far and above the best from a test ranking point of view. And after running that same single test against the RTL, we got our starting coverage number of just over 82%. And this is typical in most designs that reach close to 100% code coverage on the pre-HLS source. Running that same stimulus against the post-HLS RTL yields somewhere between 80 to 85% coverage. So there are no surprises here. Following that, we addressed some coverage holes that were introduced by Catapult's insertion of those weight controllers into the RTL. And this is accomplished by binding what are called staller modules into the generated RTL in order to force activity on those ready valid signals. This is very similar, again, to that stall injection available at the HLV level, but in this case, we're focusing on the RTL. The whole process is essentially push button from the point of the user, automated by Catapult, and as a result, we went from 82% coverage to nearly 85%. At this point, we went ahead and executed a few more tests that we had originally run against the pre-HLS source. And these were focusing on corner cases in the design that the single top rank test hadn't hit. No new tests here, just pulling more stimulus over from the work that we'd done earlier. And the result was another 5% bump in RTL coverage to 89.7%. Finally, we applied some formal techniques to analyze that post-HLS RTL for reachability via the CoverCheck formal app from Questa. Even with generated RTL, there will be cases here and there where we cannot execute the code and would ultimately be optimized away during RTL synthesis. So after applying the exclusions automatically produced via this analysis, only a handful of expression coverage items remain for a total of nearly 99% coverage. Now, to be clear, we didn't have to write any new tests, and we didn't encounter anything new or unexpected that required us to stop and do debug at the RTL level. This isn't always the case, of course, but in general, all the work that we did at the pre-HLS version level of the design paid off here. It saved us a lot of additional time and effort. All right, so to wrap up, during this session, we walked through the tools and the methods employed that allowed us to focus our verification efforts on the faster and more flexible pre-HLS source version of our design using static and formal methods, in conjunction with well-established methods such as UVM for dynamic simulation. Verifying at this higher level of abstraction yields efficiency gains in terms of earlier access to the design, faster simulation performance, in addition to giving us the ability to reuse our verification environment for sign-off by dropping in the post-HLS RTL version of our design that we already fully verified prior to synthesis. At the RTL level, only a handful of remaining items should need to be verified, all of which were added by Catapult as part of the synthesis process. And verifying those items should be relatively easy given the high amount of reuse from the original HLV effort, along with some extra simulation and formal flows that are automatically provided by Catapult. If you would like to more closely inspect the work that we did on the ML Accelerator design, you have a couple of options. Those of you with access to a Catapult install can find the full source under the examples directory shown here. But even if you don't have access, you can download everything from GitHub at this URL. Thank you very much. So we have, let's see here, it's 8:45, well, my time, early in the morning here. Are there any questions? You can type them in the chat window, and Dave and I will be happy to try and answer them.
Indeed, nice work, John. And just mentioning that when we talk about that resulting holes in the RTL, predominantly, right, we've achieved our statement of branch as John showed. We have focused expression items, condition items that remain, and we haven't gone into details here, but essentially that could be using our formal analysis tool to provide a witness waveforms on how to address those remaining coverage holes.
Well, I'm looking at the chat. Assuming I'm looking at it right, I don't see any questions. So we'll give it a few more minutes, but thank you everybody for your time and attention today. I hope you're enjoying DVCon, and thank you. I have one question here. Is there a certain class of design that lends itself well to HLS? Dave, do you want to comment on that?
Yes, I would say the distinction is we talked about here designing in System C using the NVIDIA Connections library, which facilitates not just maybe the more traditional data path that you would think of for HLS, but also provides the ability to do control as well, down to the state and cycle accurate required by protocols. For example, here we have AXI4 in a HLS abstraction. That being said, there are certainly still algorithms and approaches that are more central, more typical in HLS design flows.
Thanks, Dave. Another question came in, is my understanding correct that there was no DPI needed to interface with the C model when using MatchLib? That's correct. The pre-HLS design was natively written in System C using MatchLib connections to define all of the interfaces between blocks and with the outside world. Catapult is able to automatically produce a pin level wrapper around that MatchLib connections design, which is still in System C. That is encapsulated entirely and compiled as a System C module, which can just be dropped into any bench. It doesn't have to be System Verilog UVM. That's what we used here. It could be any other simulation approach that would accommodate RTL the same, but there was no extra DPI that was needed to facilitate communication there.
And just adding to that, John, essentially we're utilizing or relying on the mixed language capabilities in the simulator to cross that Verilog SV UVM to system C boundary.
Mm-hmm. See here. Can HLS be applied to control heavy designs such as cache controller? Will this type of high level verification be applied for memory system verification? You want to take that one, Dave?
I don't see that question.
It's about 3 or 4 up from the bottom. We're about 3 questions deep now. So it's from Imana. Oh, it's a direct message to me. Sorry, I'll didn't realize. I'll copy paste that into the so everybody can see it. There we go. Oh, sorry, my copy paste didn't work. Try again.
I'll go ahead and jump in. There's a question from Mark. Does the flow integrate well with complex sensor designs containing models of various levels of activity for the analog subcomponents? I would say to the extent that here we're using SVUVM, to the extent that you can model that type of accuracy you would need for your analog subcomponents in in Verilog, absolutely. This would allow for that mixed language, even down to that level of accuracy for analog subcomponents. I would say there's probably other approaches, other tools that would even go further in terms of the analog capabilities than SVUVM. So consider that as well.
So I'm not, my copy paste, Dave, is not working, but the question is, can HLS be applied to control heavy designs such as a cache controller? Would this type of high level verification be applied for memory subsystem verification?
Yeah, it's similar to, I think, the first question in terms of, are there certain design characteristics that lend themselves well to HLS? And I would contend that a cache controller is probably an example of a control heavy that does not lend itself well to HLS design, despite the fact that you can do control-based designs in the system C with connections. Essentially, I think of a cache controller as something that's very cycle to cycle. There's not much flexibility for the HLS to do certainly architectural exploration, or like you mentioned, John, loop unrolling or pipelining to meet your frequency goals. I would say certainly not the sweet spot for HLS in terms of cache controller. We have customers that have done it, but again, I would contend not the sweet spot for HLS methodology.
Yeah. There was a quick follow-up about the DPI question. Does MatchLib implementation work with a C++ model or just System C? This particular design was written natively in System C using MatchLib. It is possible to wrap your C++ untimed C++ design in a MatchLib wrapper to facilitate that level of connectivity. It's typically a manual process though, so we recommend that this approach rely on using System C and MatchLib connections natively in the design in order to achieve this pin level accuracy that allows us to do that reuse.
I like that question, and just admitting that that is, John, what you described is certainly a more complex usage of this wrappering flow. When perhaps for the purpose of trying not to confuse, we did a System C as the HLS design source here, and effectively it could be taking your untimed, what we refer to as untimed C++, without its native support for threads, and wrapping that in the MatchLib connections approach that we've used here, essentially introducing threads to your untimed C++. It is possible it would fall into the same reuse environment we described here, but it is a more complex use case that we intentionally didn't cover during the tutorial today.
Moving up the question here. Does the flow integrate well with complex sensor designs containing models of various levels of accuracy for the analog sum components?
Sorry, that's the question I already answered.
Oh, I'm sorry. I
We're
missed
going
that.
about
Okay.
different directions here, I think.
Okay, well, I think then the only thing left is the one at the bottom. Is there UPF support available?
I contend I don't necessarily understand. Well, I understand what a UPF is. It's not. I don't see applicable of UPF in this what we're talking about here in terms of HLS and even RTL levels of abstraction.
Typically, I mean, I guess the short answer is no, but that's typically, I think, because if we're incorporating UPF into our synthesis flow, that's going to be downstream from high level synthesis. The boundaries of power islands and whatnot would be defined, probably best defined above the layer of whatever catapult or high level synthesis tool is producing. All right, there appears to be a mad stampede out of the room. So I think we might be done here. But thanks again, everybody, for joining us today and for listening to me blather on for a while. Yeah, thank you very much. Anything else, Dave?
Yes, thanks everyone. And maybe I would just add that, where do we see this going next? And two things that come to mind is we're certain this type of approach, we're certainly very cognizant of how can we, as with any approach, perhaps get the best performance with the desired visibility, the desired accuracy. I think we have perhaps some still gains we can still obtain there. And for example, I think there's an upcoming session. I have nothing to do with it, so I'm not plugging it. But for example, assertions in HLS design source language, temporal assertions. Certainly, System C has a notion of a clock for HLS. From a verification engineer point of view, I'm excited about that as another adoption of traditional RTL approaches, only now working with an HLS level of abstraction. So thank you, everyone.
Yep. Thanks very much,
work,
everybody.
John.
Thank you. Take care, everybody. Have a great rest of your conference.
Hello, welcome to this tutorial, and thank you for joining. I'll start soon. Okay, welcome again. So